In this exercise, we have to compute this triple integral, and let's take a look at the region on which this is defined. The outer loop is x, and x goes from 0 to 1. Inside that, we have y going from minus root of 1 minus x squared to plus square root of 1 minus x squared. And less importantly, z goes from minus x squared plus y squared up to x squared plus y squared. What I'd like to do is just focus on the xy for the moment, and let's see what this gives us in the xy plane. I brought in a sketch, and I'll just say a couple of words of how I got to this sketch. Well, in general, if I just took the unit circle, that would be x squared plus y squared equals 1. And if you extract y, you get that y is plus or minus the square root of 1 minus x squared. So you would think that this might be the full circle, and y would go between plus the square root and minus the square root, except that we have that x is restricted to be between 0 and 1, so we only get the right half of it. So this is in fact the region in the xy plane defined by these two. As x goes from 0 to 1, let's say there's a typical x, then y goes from minus square root of 1 minus x squared up to plus square root of 1 minus x squared, and everything in between. And so it sweeps the semicircle as x sweeps from 0 to 1, y goes along these vertical slices, and that's how we get it. If we were working in 2D, I would just say at this point, let's move to polar coordinates because we have a circular symmetry. But we're in 3D, so the equivalent of polar would be cylindrical. Since cylindrical doesn't really touch z, it just leaves it alone. I'd just like to remark that one way of doing this question, an alternative way, and you might try it, is to do the dz integral first. All this is a constant, and that comes in front, and if it's easy to do the integral dz, and then you'll just get dy dx, and then you could do a polar transformation in just two variables. But I'll leave this as is. So not only does the region sort of beg to be done in polar, but I also have x squared plus y squared, which is a good expression for polar or cylindrical. They're both, as I say, very similar. Let me write the equations of the cylindrical transformation. It starts out like polar. X equals r cosine theta, y equals r sine theta. The differences between polar and cylindricals, we get this extra one, z equals z, which means z just stays as it is. And then we also, well, this thing here is actually dv, the three-dimensional equivalent. In 2D, we would just have dy dx, which is dA. The difference is that the dv, it's just like the dA. It's r dr d theta, except that we also have an extra dz in here. So let me just rewrite that. So it's r dz and then dr d theta.